As we know, alternate sources of natural rubber are very important, but quality is the key. Not any alternative natural rubber will do. There's 2,500 species that make natural rubber, but only a few have quality similar to the tropical rubber tree that would make good tires, for example, good gloves, all the products that we know about that require high performance. So what we do here is test the mechanical properties of our alternative rubbers and also the composition, the fillers, things like this that we put into those materials. In this particular sample, we're replacing petro-derived carbon black with eggshells as a filler. This is a new reinforcing filler we've developed from food processing waste, and it's actually very effective. And when this material breaks, the dumbbell breaks, it will tell us how strong the material was, how stretchy, and how soft. So there are various things that this particular tensiometer will be able to tell us. Now, once a sample dumbbell has been broken, we reset the machine, take the old one out, which Tony is doing now, and then you'll see him put a new sample in. So we do this for replication and also to look at the different properties created by different fillers and different formulations. This is all in support of the bioeconomy, so that we have as green a footprint as we can. So you can see he's positioning the two fat pieces of the dumbbell in the two clamps, and what you then measure is the stretch and strength of the skinny bit in the middle. Now this is an ASTM, so industry standard dumbbell. So this is what's going into that clamp, and then it's stretched like this by the machine. And with me, I can't tell what force I'm using, but the machine will measure it. Okay, so Tony's just finishing putting the sample in and clamping it in place. Then Cindy's going to set the machine going. And now you can see that it's pulling. Now with rubber, the more stress it has on it, the stronger it gets. And this is called stress-strain crystallization. But it means the more you pull, the harder it is to pull further, so it gets stronger and stronger until it reaches the break point. And that's which was right there. The tensiometer isn't the only piece of equipment we have for measuring aspects of rubber quality. So for example, if we look in this lab, you can see there's a piece of equipment there which is actually a dynamic mechanical analyzer. This looks at tiny amounts of material, and we can also look at its performance at all sorts of different temperatures. This one actually runs from liquid nitrogen temperatures all the way up to very hot temperatures. So you could see if your material is still flexible in extreme cold, or whether it melts at extreme heat, how stable are you, how broadly based can you have your applications. And then in support of the bioeconomy, this is a bomb calorimeter. It tells you how much energy is in a material, and we're dedicated to 100% crop consumption. So if there's any leftovers, what are we going to do with them? If we want to send them to energy, how much energy do they have? If we look at this next one here, this is a gas chromatograph, and we're doing this with inverse chromatography. This allows us to look at the actual properties of the fillers that we're putting into our rubber composites. This one is a preparative HPLC, which allows us to separate out chemical fractions with more detail than the ACE can do. So I can look at individual compounds that are in our rubber for one reason or another, so that generally that are naturally occurring and come to the compound with the rubber itself. But this will also allow us to purify enough of them that we can do some proper testing of what their role in the rubber compound actually is. Is it good to be there, or is it bad to be there?